So, till now we were talking about mostly the martingales, correct, because the martingales and its quadratic variation. Now, these martingales would constitute to be your integrator, because that is the main purpose, but we would like to integrate some integrand, okay, some process. But every such process, every arbitrary process would be integrable with respect to a given martingale is too ambitious plan. Okay. So, that we might not be able to do. So, we should start thinking about what are the processes which can be integrated with respect to the martingales. Okay. So, we are now going to look at the space of integrands. Okay. What are the suitable space of integrands one should look for. Okay. So, let me since I am just talking too much, maybe I should keep this thing written somewhere. So, we are talking about integration of x t, so dmt 0 to t. So, this is integrand, this is integrator, and this whole thing is integral, correct. This whole thing is integral. Okay. So, now I mean till now I was talking about this martingales etc. Now, I focus on integrands. Okay. Basically, you have to talk about space of integrands and appropriate norms etc. So, let us consider a measure that is on the set of time and omega. So, we consider A to be a Borel set from the product sigma algebra of Borel sigma algebra on the time axis, so 0 to infinity, and A for on omega. Okay. So, we take such A, because for process I have two variables, okay, t and omega. For so, A is actually set of t omega points, okay, but a measurable set with respect to this sigma algebra. So, for such A, mu m of A is defined in the following way. Why mu m? Because given m. So, after fixing m, we consider this measure mu m A. So, that is defined as expectation of integration of indicator function of A with respect to the quadratic variation of m. So, when I fix m, I have fixed quadratic variation of m. Quadratic variation of m is an increasing process. So, I can define integration of something simple, okay, something easy things with respect to a increasing process. And so, how do we understand this integration? I would think that okay, I would fix omega first. If I fix omega, then dmt is an increasing process, and then for that fixed omega, this 1 at is also a functions, okay, if a function of taking only 0 and 1 value, basically indicator function. Since A is measurable, so section omega section of A is also measurable. So, this function is measurable, and since it's bounded, so and this m is need not be bounded. However, so but it is increasing and this is non-negative. So, it can be infinity sometime, does not matter, we can still give the notion of integration. So, this measurable function, non-negative measurable function, we can define this have the it has usual meaning of this integration 0 to infinity where time is moving. So, now for every omega we are getting a number which is real number, okay, positive real number, otherwise it is possibly plus infinity. Okay. But then we take expectation. So, before taking expectation, it behaves like a random variable. Okay. So, this is like Fumini's theorem kind of thing. You can say that okay, if it's omega section, so then this integration is also measurable with respect to omega. So, measurable function is omega. So, this is a random variable. Now, we take expectation, basically repeated integration, correct. So, here that second is you are doing the integration with respect to p measure. Okay. So, then whatever you are going to get is surely a non-negative value. okay, and it could be positive number or plus infinity. So, this would be a non-negative extended real number valued map. So, mu a defined this way clearly satisfies all the conditions for this to be a measure on this sigma algebra. Okay. So, this mu m we consider, okay, and then we use this mu m, okay. Actually this mu m is used only at this place to define an equivalence relation. We call that x and y are equivalent if x and y are equal almost every mu m, in this sense of mu m. Okay. If they are almost equal almost everywhere with respect to the measure mu m, then we call x and y are equivalent. Okay. So, now we agree that here this equivalence is depending on m. After fixing the martingale m, then we talk about that the space of integrands and their equivalence. Okay. So, this is very important thing to remember. So, for a measurable ft adapted x, okay, so assume that we have a stochastic process x which is ft adapted and measurable. Okay. So, define this norm. Okay. So, we call that the square bracket x t square is equal to expectation of integration 0 to t x t square d quadriviation of m. So, we take integration of x square with respect to mu m and probability measure. Basically, this is correct. It is basically with respect to mu m and probability measure with two measures. So, repeated integration. So, that is x t square. So, if you take square root both sides, then you get square bracket x subscript t. So, the definition is such that it is a norm. Okay. Now, we define this class, we denote it by the script L of m. So, given m, okay, we define this class of integrands. So, we say equivalent classes of measurable and ft adapted processes x such that we get this norm finite for every positive t. So, earlier remember that we found out this by fixing a capital T. But when we talk about integration, we do not need to just consider a finite horizon, finite time horizon. So, for every positive t, we take, if this is finite, then we include that in this space, okay, L of m. Now, we endow L of m with a particular matrix. So, this square bracket t norm is insufficient, it is not appropriate, because this is appropriate only when x time only 0 to t is considered, capital T is considered. So, here we define this particular manner that x box n, okay. So, this square bracket n minimum 1. So, if that number, this value is more than 1, we replace that by 1 and divide by 2 to the n, and n is running from 1 to infinity, this sum, this infinite sum. This infinite sum of course converges, because the numerator is always less than or equals to 1 and denominator is 2 to the n. So, this is dominated by a geometric series. This series value is taken as distance of x from 0. Okay. So, this L m box would serve as the space of integrands, okay, of for a stochastic integral with respect to a given m. Next, we define, so we cannot actually straight away define this integration for x coming from L of m. Okay. We cannot do that, we need to build it step by step. So, we start from the very fundamental and simple thing. Okay. So, a process which looks like this, like step function, correct. So, let us read it. What is it? For every omega, this is like that xi I of omega would be a real number, and then you are considering open interval ti to closed interval ti plus 1. So, this is a step function and I is equal to 0 to infinity, but it has possibly infinitely many. So, it is a step function basically has the finitely many things. So, it is not a step function in that sense, but it has only countable many discontinuities, and you have this process which you call simple process. Okay. And then for omega dependency, we must assume some sort of measurability condition. What is that? We look at it that for every t between t I to t I plus 1, the process x picks up the value xi I. Okay. So, if I need to put some measurability condition, I should put measurability condition xi I. So, we required xi I to be f t I measurable. So, then as a result, what I am going to get is the x t is f t measurable. Why? Because x t is always the t is between some t I and t I plus 1, and that is f t I measurable, and f t I is subsigma algebra of f t. So, we get x t is f t measurable as a result of this. Okay. Xi is f t I measurable, and then third thing is that we require xi to be a bounded random variable. Okay. So, supreme over all I and supreme over all omega is finite. Okay. So, we just need xi to be bounded random variable. So, I mean nothing simpler than this can be considered as an integrand, although this is a very small class, but we are going to see it is not that small. It is actually dense in a very large class. Okay. So, one can approximate a useful integrand using members from this L0 class. Okay. But in which sense and which way, that we are going to describe in the following two slides. So, L0 is called the class of simple processes. So, we write down this result. Let x be a bounded measurable f t adapted process. Okay. And then there exists a sequence of x m from L0 such that you would get this expectation, okay, goes to 0 as m tends to infinity. Okay. So, what is this expectation? This is integration of x m minus x mod of x m minus x whole square dt. Okay. And time t is running from 0 to capital T, but we are also taking supreme over all possible capital T. Okay. So, in this consideration, the martingale did not play any role. So, we are not integrating with respect to the quadratic variation of m, we are only with t. Okay. So, here for L0 also we did not put any condition, it is not dependent on m. Remember earlier we chose L of m. Okay. So, depending a martingale we defined what is L of m, but L0 is like universal, correct. It is, you do not care anything, you just have a filtration from the, with a given filtration you come up with L0. Okay. And since this is a result of L0, so we appreciate this this result, that here we get that mod of x. So, we can approximate. So, this basically says that, so in this square, this is actually L2 norm, correct. So, because we are taking square and integrating with the time, and then integrating with the probability measure. Okay. So, this is L2 norm in lambda cross p, where lambda is the Lebesgue measure on time, correct. So, it is saying that, okay, that thing L2 norm is, but here supremum capital T greater than 0 is also involved here, but if you fixed capital T, that means you are just considering only finite horizon case, then it is just saying that, okay, unified horizon case, every bounded measurable f t adapted process can be approximated by a simple process from here. Okay. So, that is a nice result. Now, we proceed further. If we have m square root martingale such that it has a nice property. What is nice property? There is a typo, this t should be outside. Okay. So, if t to mt, okay, coefficient mt, this map is absolutely continuous. Okay, if it is absolutely continuous, almost surely. Why almost surely? Because this map is also depends on omega. For every omega you get different maps. Okay, but you observe this map to be absolutely continuous with probability 1. Okay, that I mean by absolutely continuous almost surely. Then L0 is dense in L of m. So, what is the bottom line? The bottom line is that I cannot assure L0 to be dense in Lm for any arbitrary m, only if m satisfies some nice property. Say m is such that its quadratic variation process, which is the increasing process, is also absolutely continuous. One can just ask, actually any analysis student would know that there is a very pathological example which is increasing continuous function, but not absolutely continuous function, correct. You know it, Cantor-Ternary function, correct. So, one can define that Cantor-Ternary function which is increasing continuous, but not absolutely continuous. So, of course, there are plenty such functions which might not satisfy this condition, but if such condition is true that it is absolutely continuous, then we know that this result says that L0 is dense in Lm, or in other words, if we take closure of L0 in this norm, then Lm is this L0 closure. Okay. Now, the other side, if T to MT, this map is need not be absolutely continuous, but continuous, it is just continuous, then what can we say at most or at the best? Then this closure of L0 in this norm, may not be equal, but of course subspace of Lm, but any x, if it is in Lm with right continuous or left continuous path, that is in L0 bar. So, closure of L0. What do I say here? I say here that this integrands which has a nice continuity property, like it is either right continuous or left continuous, then that can also be approximated using L0 bar. Now, we see some more definitions. So, L star m, what is L star m? L star m is nothing but the set of all x in L of m, such that x is progressively measurable. So, what is the use of L star m? Basically, here we just could assure that it is just a subset, but we could not categorize what it is. So, next slide we are actually categorizing what it is. So, now L star m we consider as x is progressively measurable, that means you put some more condition on x. So, x is L in L of m is one condition. So, it is in this large class, but you put a additional measurability condition on x, that is it is progressively measurable. Then L star of m with this squared bracket norm is a Banach space. So, and it is subspace of Lm, closed subspace of Lm, and L0 is dense in L star. So, this L0 closure is nothing but L star m. So, if we need to define integral for an m whose quadratic variation need not be absolutely continuous with respect to time, then I should consider integrand not from Lm, but from L star of m. Why? Because if I consider from L star m, then I can approximate this using that L0 space, and perhaps that would allow me to give a meaning to this integration, but I have not come to that point yet. I would come to that soon. So, now we define what do we mean by stochastic integral for L0 process. First we define that, and then we are going to extend this notion for the larger class. We are going to extend this map. So, this is a functional, correct, because it. So, we write down this it. So, given x, okay, and of course m is already fixed. So we define it of x for every positive t in the following manner. This is an integration 0 to t, this is the notation, okay. We write down this way, 0 integration 0 to t xs dms, this notation. What does this notation mean? It means that means this this summation, this is xi m t minimum ti plus 1 minus m t minimum ti, okay. Why does it come? It comes if we just consider this integration and we see that in an interval of time ti to ti plus 1 xi is fixed, and for that if I integrate just such constant random variable with respect to a martingale mt, I do not know what should be the notion of the integration, but whatever it is, if it does not give me that xi times mti plus or minus mti, then that notion I would not call as integration, correct, because for integration of a constant with respect to integrator should be difference of the integrator multiplied with the constant, okay. So from that point of view, I should consider integration of such process with respect to mt as mti plus or minus mti times xi and sum over all xi. So that is the only natural notion of integration. So we are accepting that notion and we are fixing that notion, okay. So integration of this is defined to be, this is not a result, we are not proving, this is the defining, we are defining this to be the sum of xi mt minimum ti plus 1 minus mt minimum ti, okay. So where does it belong, what is it, okay. So let us see, now we would extend this map. So here first we must understand that if we take such kind of norm, okay. So here m, I mean this norm of m for a fixed t given a square root of expectation of mt square, this is nothing but L2 norm, correct. So for a fixed t, L2 of p, L2 p norm, correct, the probability measure. So square of expectation of square and then square root. So this norm we are going to talk about for fixed t, okay, and then for the whole time horizon we are going to take only t which are natural numbers, okay. Why should it be sufficient, that we are going to see later. So because here this norm, when we consider, we are not looking at what happens to the process between 0 to t. Here this came only for the process at time t. So for each and every uncountably many different t, there are many informations, okay. So when you consider this, one can think that okay, many other informations are lost, okay, we are not considering those, but that is not the case, because we know m is also martingale. So from that we are going to get some inherent relationship between times, okay. So this way I am emphasizing it because one may get confused what is the difference between this way. So here in this way, when you write down capital T, that took care of the process x from 0 to capital T, correct, actually captures the behavior of x for throughout the time, okay, throughout this time. But here it apparently it is not, okay, apparently superficially it is not, okay, but actually it does. So that I am going to show later. So now we would extend the map x to ix, okay, to this end. What we need to introduce the norm. So here m is like square integrable martingale, and then we know that this is finite, expression mt square is finite. So this is a finite number, and we can consider this as distance of m from 0, okay, because these are all less, numerator is less than or equals to 1. So this series converges. Note that this xt is increasing as t increases. This is the first thing to note. Why? Because the reason is that mt is martingale, mt square is square of mt, square is a convex function. So, convex function applied to a martingale gives you a submartingale. A submartingale's expectation never decreases, keeps on increases. Okay. So, that shows that this m subscript t, the norm of m subscript t is never decreasing, so ever increasing. So, that is the first thing to observe. Okay. Now, fix s and t, so the s is less than t, s is positive. So, now norm of x square, okay, so that is by definition is expectation of x square, and that I can write down x's I can replace by a conditional expectation of x t given f s, okay, because you know x is a martingale. So, this would be expectation outside, but inside conditional expectation of x t given f s, but square is there. Then I apply Jensen's inequality to the conditional expectation, then I get less than or equal to sign. Why? Because convex function of average is less than or equal to average of the convex function. So, here expectation of x t square given f s. So, this double expression is give me only expression x t square, and that is norm of x t square. So, what we get is that norm of x square is less than or equals to norm of x t square. Okay. So, this is also the same thing as noted before, like with the submartingale, it is proved here also. We need to show that if x and y are in M2, the square integrable martingale, such that like distance of x and y is 0, then x and y are indistinguishable. Okay. So, this is something we need to establish. If we do not establish this, then we do not know that what is the equivalence class to fix, so that this functional that we have introduced gives a metric, because it is apparently it is not clear, because it is just considering value of m at some integer points, not taking in between. So, in between what happens, it is not showing anything, but what is showing 0, but the process is not 0. Okay. Then t is not a metric. Okay. So, for that we need to understand this part. So, assume that distance of x and y is 0 implies is that this nth norm of x minus y is 0 for every n from the very definition, because if this is 0, that means each and every term is 0. So, every m n is 0. So, this thing is 0 for every n. What does it mean? That x n is equal to y n almost surely. So, with probability 1 they are exactly equal. Okay. So, then what we do is that for a given t we consider n next to it, the smallest greater integer, the ceiling function of t. So, thus x t can be written as conditional expectation of x n given f t, but x n and y n are equal almost surely. So, this is same as expression y n given f t. Okay. So, this is a typo, this is f t, it should be f t, and that is, since y is also a martingale, so we are going to get that is y t. So, we are establishing s t is equal to y t almost surely. Okay. So, for every fixed t, x t and y t are matching with probability 1. So, that means x and y are modification or version to each other, but we need to prove this is a these are indistinguishable. However, we have extra information that x and y are right continuous. Okay. Since x and y are right continuous, then we get that they are indistinguishable also. Okay. Fine.